All right, so we're going to go over problems from chapter 7 tonight. All right, and well, we can get started. Okay. Let's see, I guess I'll go to the book first. All right, so this is the ebook, and let me find out what page we're on. All right, this is page 211 in the textbook, and it's problem 7.9. So why don't you try 7.9, see if you can actually do these problems, and then we'll go over them. If you can't, then I'll go over them myself. Wait a minute. Right. Oh, I see. All right, how you guys doing? Almost there?
I haven't finished yet.
Yeah, neither have I.
You're using Minitab or Excel for this? All right. Well, let's get started. Okay. For A, what is your answer for A? You don't need any calculations for that one. You don't, absolutely no calculations required. What's the answer?
50.
50%.
0.5.
0.5, yeah, because it's the
Oh,
median.
Yeah,
It's the median, right? Yeah. The mean's
Right.
equal to the median, and if you're asking for greater than or less than that value, it's always 50%. All right, how about B?
0.683.
Okay. How about C?
0.8.
You got to give me more digits.
8415.
0.8415 should be 13, but that's okay. How about D? What's your answer for D?
I didn't get that one.
0.
I didn't get that one.
Wait. What's the answer? 0.
Why?
Don't you read? Because it's a continuous random variable, and it's saying equal to. The answer,
Okay.
I don't. You can take.
Oh,
If it's equal to for a continuous random variable, hey, put any number next to that. It's 0,
Mm.
right?
right.
You could put the letter A in there. A meaning any real number is 0. All right. How about E?
Uh, 0.955.
E?
Again?
No.
I got
0.955.
Oh,
0.475.
yeah. I see what I got wrong.
Yeah, it should be 4.4772. How about F?
Yeah, half of.
What's F? X is greater than or equal to 16.
0.042.
0.042.
42.
That for F?
Yeah, for F. You're saying
Uh,
0.042?
I got
No, sorry.
0.975.
90. Sorry, the opposite of that.
96.4%.
So 95.8.
I don't know where you're getting your numbers from, but let's look at Excel here. Because you're a little bit off, so I'm not sure where you're getting these numbers from. So the mean and the standard deviation, you're using Excel, just put in the mean and standard deviation in different cells. We call, mean, standard deviation. That way you never make mistakes with this, all right? Then you set up the norm distribution, norm.dist.
Professor, are you working on the
Oh, I'm
Excel?
sorry. Yeah, I'm sorry. Forget it. No, hold on a minute. You don't see it, do you? All right, let me get to Excel here. Now you see it, right? You see it now?
Mm-hmm.
Yes.
All right.
Right.
So the mean, you just create two cells. You just have the mean and standard deviation in two of the cells. That way you can reference it. You can change it at any time too. All right. This will just save you some time if you're using Excel. The first one here, I'm subtracting two normal distributions. One from 20 to 30. I'll put the normal distribution starting at 31st, but 31st, F-I-R-S-T. So third, and then I put the mean, standard deviation, and I put true in here for cumulative. Cumulative meaning what? Less than or equal to. So between 20 and 30, you want to subtract the 20 from the 30, right? Correct? So you subtract the normal distribution for 20, all right? And you'll get between 20 and 30. So you get your 0.682, 683 if you round in 3 decimal places. But you'll get the exact answer here. The next one said less than or equal to 30. I think this one right here. Then for between 15 and 25 is this one here, put 25 first and subtract 15. Now, one that says greater than or equal to 16 is 1 minus less than or equal to 16. If I do 1 minus the normal, that's 16. It gives us 0.964. All right, can you see it okay? Seeing it okay?
Yeah.
Yeah.
I have a question. I was using the area provided by the book.
No,
So
don't do
it's
that.
like
No, don't do it.
60.
Don't
Don't
do
do
it.
that?
No.
Okay.
Why? This gives you the exact answer. Don't use table. As I said in the last class, tables were for people who was pre-calculators even. Don't use the tables. They're backups in case your computer explodes and your calculator, you drop it and it cracks in half or something. I mean, you don't need it. The tables. The tables are approximate anyway. They're not exact.
Okay.
Go with this. This is so easy. Why bother with the table when you can just do this? You just type in NORM and then you do equal NORM and then you'll see the choices and this is the one you want to choose, norm.dist for normal distribution. Okay? So I showed you last time how to use Minitab. And Minitab's kind of clunky, right? Excel is so easy to use for this. You might as well use Excel. Now, Minitab, will have its advantages when we start doing inference. You might be able to do inference better than Excel, if possible. But Excel, for what we're doing here, is perfectly fine. The best thing to do is using one of these things. Then you don't even have to subtract normal distributions. These things gives you the exact answer without doing very much at all. Do you both have one of these? 83, TI 83, 84?
No.
Yeah, really easy. You just go to second, DISTR. second DISTR, and you end up with the list of distributions here. And then you, for normal, it's just, it's option 2. You never use option 1, normal CDF. Then you put your lower, your upper, your mean, and standard deviation. So easy. But I'm teaching Excel because you can do it easily in Excel also. Yeah, I mean, when you have this problem here, the last one, probability x is greater than or equal to 16, you literally put your lower endpoint in your calculator. You put your lower endpoint is 16, your upper endpoint, pick some large positive number like 1,000. Put your mean and standard deviation, hit enter, and you get your answer. But again, I'm not teaching this. It's not even part of the course is to have this calculator. But you can look up how to do it on here. It's really, really easy. So you can do that. I mean, Han, you don't have one of these, right? You don't have this, right?
No, I can use Excel.
Excel. Excel's fine. Minitab will do everything that's on here for sure. And Excel will do this. I think this is just a little easier to work with for this, Excel. All right. So do you get the idea of how to set it up in Excel? Just have your 2 cells there.
Mhm.
I mean, to be honest with you, I can change right now the mean and standard deviation, leaving the problems the same. Let's make the mean 100, standard deviation 10. Well, no, I shouldn't do that. Let's make the mean 22 and the standard deviation 8. 22, 8, and all your answers change. Okay? So it's a good idea, I think, for the normal to use in Excel, use cells for the mean and standard deviation. Just put the numbers right in there. That way you don't make a mistake, right? Because otherwise you're going to be repeating those same numbers and you could easily make a mistake. And this cuts down on the number of mistakes you can make. All right? So just, okay. Now let's look at 7.11. This is sort of a word problem. So it's on the same page. And to be honest with you, in word problems, unless it's a very complicated situation, it's pretty much blah, 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 mean, blah, 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 standard deviation. And then they ask, what is the probability, blah, 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 right?
Right. Yeah.
Right. Like people say, I don't like word problems. Well, just instead of reading the words, just say blah, 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 and it's fine. It'll get the same. You get the answer anyway. So try 7.11. And I'll do the same thing here. All right. I just use the same Excel cells again to do this. All right, guys. Let me show you how I did in Excel. Again, I just changed the mean and standard deviation to what the problem said. 360,000 for the mean, standard deviation 30,000. This formula here is the answer for what? B. You know what A is, right? A is 50%. So forget about that one. B, between 400,
50.
yeah, between 300,000 and 420. So I put 420,000 first. I put 300,000 second, and I get my answer is 0.9545. For C, I just changed the upper one from 390 to 390,000, lower one to 330,000, and I get 0.6827 if you round to 4 decimal places. And then the last one, I already have this set up 1 minus because it says greater than. So it's going to be 1 minus less than, right? So 1 minus less than, I put 270,000 in for the value, and I get 0.9987 if you round to 4 decimal places. You can see it's pretty easy to do it in Excel, right?
Yeah.
Especially when, you know, it's kind of written for you, you know, it's all set up for you pretty much in the problem. I want to show you one thing before we move on. Where is it? This here. This is going to be the solution page, by the way. Let's move this out of the way. This symbols here, let me tell you what this means. Instead of writing out X is a normal distribution with a mean of 25 and a standard deviation of 5, typically people write it this way. X is the random variable. This wiggly thing here means distributed as, right? As what? N, normal. First number inside the parentheses is the mean, comma, standard deviation, close parentheses. And you see N, 25 comma 5, you know it's a mean of 25, standard deviation of 5, okay? So if I say this in a test, you'll know what it means, all right? We're using the random variable X in this case here. Here, we said X is distributed as a normal, mean 360,000, standard deviation 30,000. Okay. And notice in 711, it doesn't say probability. It says what proportion of the mortgages were. Remember, probability can mean two things. You select somebody at random, say what's the probability that person has values between whatever. Or you could say what proportion of the population has these values. Means the same thing.
Mhm.
So if you say proportion, no, it means probability. Okay, that's why I wrote it out this way. Okay, let's go to page 221, 7.17.
You said 7.17?
Yeah.
Okay.
Now, this one is where we have to think in a backwards way, right? We have to think backwards in this case. Now, remember, in Minitab, there's a function in there. Or let's say there's functionality in Minitab that allows you to calculate the value from the probability, from the cumulative probability, right?
Right. Yeah.
All right. How about Excel? Does Excel do that? Does Excel do that? And yes, there's a function called norm INV, NORM INV. That's called the inverse norm. So that's what you're going to use to calculate the answers in 7.17. So I want you to try that without any prompting from me. I want you to try it. And again, I'm going to use the same cells for mean and standard deviation. Now it says standard normal. What is the mean and standard deviation of a standard normal? Remember?
Not off
What
the
is
top
the
of my
what,
head, though. No.
what is the yeah, you got to remember what a standard normal is. It's the z's. Remember? We can convert the x's to z's. So what is the mean and standard deviation? You got to memorize it.
0. 0.
0 for the mean. What's the standard deviation?
1.
That's right. 0, 1. So it's n. You know, if I said z, and I do the wiggly thing, I would put n for normal, and in parentheses I would put 0, 1. That's a standard normal. Okay. All right. So that's what I'm going to do on my Excel spreadsheet here. So I'm going to put 0 for the mean and 1 for the standard deviation. All right. And now I'm going to use this inverse norm thing. So I want you to try it. It might be a little difficult at first because you're not used to thinking backwards. We'll try it. And Han, you don't have the calculator, so unfortunately you can't use the calculator to do this. It's easy with a calculator, but try it anyway in Excel. If you want to use Minitab, I did show you last time how to do it, but we're going to use Excel this time for this. So I'm going to put the inverse normal below here, I think. Right here. It's norm.inv. When it says probability, it's asking for the cumulative probability. That's the probability that's less than or equal to the number that you're trying to find. Okay, give it a shot. Now, one thing I have to tell you is that if you're referring to these two cells here, make sure you put your dollar signs next to both the column letter and also next to the row number. So it always, wherever you are on the spreadsheet, it will refer to those cells, to the mean and standard deviation. I'll show you what I mean in a minute. This might be a little difficult for you, unless you're familiar with these terms. All right, how you doing? Or are you stuck?
I have an answer.
For all three? Okay, go ahead. How about
So
for
go
part
ahead.
A? Part A, Steve, go ahead.
Negative 0.67449 and positive 67449.
Okay, how about B?
Negative 1.28155 and positive 1.281552.
Yeah. And how about you, Han? Did you do the C?
No, I think I did. I didn't do it right.
Okay. And go ahead, Steve, for C.
Negative 0.73885 and positive 7.738847. I guess it's just rounding for one of
Yeah.
them.
Now, let's think about the answers here. Now, quartiles, we've learned when we were talking about the 5-number summary and box plots. Remember that? We said the lower quartile has 25% of the data less than that, which means it's a 25th percentile, which means its cumulative probability is 0.25.
Right.
So when you do an inverse normal, in this case, it's norm.inv, you're going to put 0.25 in for the first quartile. When we say lower quartile, first quartile means the same thing. And then you put in your mean and standard deviation. The answers that we get here are Z's, Z-scores. They tell us how many standard deviations we're away from the mean. Now remember, for a standard normal, the mean is 0. So when you get negative 0.675, let's just round it, or 674, that means you are approximately 3/4 of a standard deviation to the left of the mean. Okay. Now notice that the third quartile has the same number but positive. Same number, but it's positive. Now why? Steve, why do you think that's the case? Why do these two numbers match, but one is negative, one is positive?
Because these scores diverge from the mean, but it just measures the divergence and it gives a sign. So it's basically the magnitude and direction of the deviation. So they're equally deviant from the mean, just in different directions.
But why are they? And that's my question. Not that they are, but why are they the same distance away?
Oh wait, could you ask that again? It kind of broke up. Could you just repeat that, please?
Why are they the same distance away? I don't want an explanation that they are. I want to know why they are.
Why
are those two numbers? Why are those two numbers the same? One being the negative of the other. Why are they that way? It's not a coincidence.
They're both 25 away from the middle, 25% away.
Okay, you could look at it that way, sure. But we can also say the normal curve is symmetric.
Mm-hmm.
And the left tail is 25% cumulative probability, and the probability to the right of the third quartile is 25%.
Mhm.
Okay, so your reasoning's correct. I want you to look at it in terms of tails now, because some of the problems will be asking questions about the tails. So
Right.
the tails are equal. And that means the distance from the mean to those values are equal to each other. That's the reason. Now you're right. You could say, oh, well, 25%, 25%, and that's not always true though, because skewed distributions wouldn't be true. That wouldn't be true for a skewed distribution.
Right. Right.
The real reason is because of the tails. The tails are equal to each other. I want you to think in terms of tails instead of the actual distance, all right? The tails are equal because of the symmetry. So how about the second one? First and ninth deciles. Now deciles means what?
Like 10% or 1/10.
Yes. Now you know that there are 4 quarters, right? That there would be 10 deciles. So you're breaking everything up into 10%. Okay. Now you only need 9 of them, right? You only need 9 of them because, right? You don't need the 10th one because the last one is what's bigger than the, the last 10% is what's bigger than the 9th decile. So the first decile, which measures 10% less than that, and the 9th decile, which means 90% less and 10% greater, they also are symmetric because the two tails are equal to each other. Both tails are 10% of the curve, right? The first decile has 10% to its left. The 9th decile has 10% to its right. And that's why those numbers are equal. It makes sense?
Mm-hmm.
Yeah. And it's what, negative 1.28, right? Negative 1.2816, whatever the number is. Same thing with the last one too. The last one is the 23rd percentile and the 77th percentile. So the 77th percentile is 23% to its right. So that's why those numbers are opposites of each other in terms of sign. They're the same number, but opposites. Okay? 0.73, negative 0.7388 for the 23rd percentile, and positive 0.7388 for the 77th percentile. Both of those, the tails are equal. All right? So those days match also for that reason. Very important to start thinking in terms of these sort of symmetries, because when we get to confidence intervals, you might have heard of the term confidence intervals. We're going to be, we're dealing with symmetric things like this. So it's good to start thinking in these terms. All right, let's look at, you have any questions about 7.17? Not so bad, right? Once you understand, what you're really trying to find are those values of Z, in this case here, that correspond to those areas to the left of it, okay? And that's called an inverse function. Just like in algebra, we have inverse, right? We have an exponential and a logarithm, they're inverses of each other. And these are also considered inverses. This is more of an inverse in operation, in the way we're operating, right? One, we have a value, we find the cumulative probability. The other one is that we, giving the cumulative probability, we find a value. That's what the inverse normal is. All right. The next one would be 7.19 on the same page. You could try that one. This one is not a Z. Now we're dealing strictly with the X. We're not being asked, well, actually it says here, to convert each of the following values into its corresponding Z, right? So I didn't actually, did I do that? Yes. So in 7.19, I want you to convert each of these into their z. So go ahead and do that. That's an easy question. Just use the formula for the z-score and convert each of these values into their z-scores. Then let me know what you come up with. All right. You guys ready?
Yep.
All right. Let me some reason I'm having issues with hold on a minute. There we go. All right. So I guess we'll take a look at the results here. Tell me what you got for 7.19. Go ahead.
A, I got -2.
Go ahead.
B, -0.8. Or B, C, 0. D, 3.4, and E, 4.6.
Good. Okay. So that's good. All right. All right. So how about 7.21? That would be on the next page. 7.21. I want you to find those probabilities using the standard normal. So let's share the screen again and go back to the book. Oops. Like there's an issue here. All right.
You said 7.21.
21. Yeah.
Okay.
Yep. It's the one I want you to work on. There are 3 probabilities that you need to find. Oh. All right. Again, if you use the setup in Excel that I did, it just takes a second to set them up, right? You can have one of them set up for a difference between 2 normals, have one set up for less than or equal to, and have one set up for greater than or equal to, all right? That way you can just reuse these 3 cells over and over again. So what'd you get for the part A?
I'm still working on it. Sorry.
Still looking? Okay. Han, did you get these?
Yeah.
All right, we'll wait for Steve then.
Mhm.
All right. Did you finish A, part A, Steve?
I'm having trouble figuring out what to use, what Excel formula to use.
Let's use the formula we've been using. The normal.dist. Just change the mean and standard deviation to 0, 1.
Oh, okay.
The standard normal. The random variable z, if you see it, it means standard normal. Okay? That's automatically, you say 0, 1. Hold on 1 second, guys, while you're waiting. My daughter's calling me. What, Mandy? Mandy? I'm teaching the class. You want something? All right, guys. Sorry about that. My daughter's giving me an election update.
Mm.
All right. So I think I was in Excel. Can you see Excel right now, Han? Can you see it?
No.
I think once I leave the screen, it kind of disappears. Okay. Can you see it now?
Yes.
All right. So the key to do these problems is, this is the way I would set up Excel. I would, again, do the mean and standard deviation, put the mean, and now if it's a standard normal, the mean is 0, standard deviation 1. And then I would set up 3 cells. One that does a difference in probabilities, one that says less than or equal to, and one that says greater than or equal to, 1 minus the normal. All right. So part A would be the difference, right? Because it's between 0 and 1.1. So I'm just going to put a 1.1 for the upper value and 0 for the lower value, and then I hit enter and I get my answer. So you just set this all up ahead of time, have it all ready to go. The second question is a greater than question, which is this cell right here. This is greater than, I'm sorry, wait a minute. 1.35, right? Greater than 1.35? I have the wrong numbers in here. It should be 1.35. Am I right? No, it's less. No, it's less than. I'm sorry. I got the wrong one here. Sorry about that. Looking at the wrong one. All right. So the second one was greater than 1.1. That's this one. Or this, excuse me, this one. That's greater than 1.1. The answer is 0.1357. And then the other one says less than or equal to 1.35, which is this one. Let's put the 1.35 in. Make that 0.9115. So I just set up the 3 cells. That's all you need, right? For these problems. This is the in-between two values. This is the less than or equal to value, and this is the greater than value. Make sure you have 1 minus the normal.
Mhm.
Okay. Just make sure that when you put the cells in, which are the mean and standard deviation, you put your dollar signs next to both the column number or column letter. That's where the mean and standard deviation are, and also 1 to the left of the row number where they are. That way you can be anywhere on the spreadsheet. You don't even have to think about that it's pointing to the right cells. You just make sure it's set up that way. All right. I put all of the inverse normal ones here. I put the probability questions here. Steve, are you okay with that?
Yeah, I'm okay with that.
All right. And Han, I think you already have this set up, right? These were the answers you got, Han? Yeah. Okay. Why don't you try?
Yeah.
Good. Why don't you try 25? Try 25. And it does say standard normal here, right? So if we're dealing with these, standard normal. Use 0 standard mean, 1 standard deviation. Give these a shot. See what you come up with. Give you a couple minutes for these. Did I say 7.24 or 7.25?
2.5, I believe.
5.
All right. That's what I want you to do, not 240. I was doing 240. Some strange reason. I'll give you a couple more minutes and then we'll go over those. All right. Now, I'll just go over the logic behind it and then we'll look at Excel. This is a standard normal. So these are Z's. And what we're trying to find, we're given the cumulative probability. Cumulative probability always means what? Less than. Probability that Z, in this case, is less than some number. So when we say find the cumulative, if the cumulative area to Z is 0.70, that means area to the left, or percentile. All means the same thing. This is the 70th percentile. Okay, so the area to the left is 70%. That's what A is asking for. It's find that value of Z where the area to its left is 70%. Right? Same thing with B. B, it says cumulative area is 0.10. That means find the Z where the area to its left is 10% or 0.10. C, now C is making things more complicated than it really is. It says the area Z in negative infinity. Well, that just means it's the area to its left, doesn't it? It's a cumulative area. Negative infinity is to the left. So it's asking for the area to the left. It's just another way of saying area to the left. D, when it says between Z and positive infinity, it says it means area to the right. That's all it means, area to the right. So now, if the area to the right is in D is 30%, what's the area to the left? Area to the 70%, and that's the same thing as A. The answers for A and D should be exactly the same value. The area to the right is 30%. That means it's the 70th percentile. And that's what A is asking for also, the 70th percentile. It's the same answer. Right? That's what it means. Okay. So don't be fooled by it saying negative infinity or positive infinity. It's just telling you which direction the area is in. That's all it's saying. So it's all it's telling you. All right, cumulative area goes towards negative infinity. The other area to the right goes towards positive infinity. All right, let's go to the Excel. So here are the answers right here. This is the answer where we're asking for the cumulative area being 70%. You simply put in 0.7 for inverse normal here. You put 0.7 for the probability. The probability they're asking for is the area to the left. You put 0.7 in there. This one is, you put 0.1 in. That's the area to the left. Cumulative area is 0.1. This one here says the area to negative infinity. Well, that's area to the left. That's 0.54. The area to the left. I just put 0.54 in there. And this one, they're saying the area that goes to positive infinity is 30%. That means the area to the left is 70%. It's the same question as the part A. It gives you the same answer, 0.524. I want you to become comfortable with finding these Z's that have various areas to the left and right of them, because we're going to be actually using this in the next section when we do things like confidence intervals and things like that. We are going to be using this technology that I'm showing you. All right. Now, 7.33 is on the same page. It's a word problem. I want you to take a look at it. Actually, let me read it with you. 7.33, this is on page 222. It's been reported that households in the West spend an annual average of $6,050 for groceries. Wow. I think I spend that in a month. All right. Assume a normal distribution with a standard deviation of $1,500. So your mean is 6,050. Your standard deviation is 1,500. Part A, what is the probability that a randomly selected Western household spends more than $6,350 for groceries? All right. So maybe I'll work. Let's work on these together. Let's do this together. You're you're looking at the Excel spreadsheet right now, so I think maybe we should just do this together, so we don't stay here to midnight. So I'm going to put my mean in as 6,050. And I'm going to put my standard deviation as 1,500. Over here are my probabilities. On the first one, I want to know what's the probability that I spend more than 6,350. Well, this is this cell here, 1 minus the normal. Remember, the normal gives you the cumulative probability, the probability that's less than, and they're asking for more than. So I'm going to put 6,350 in for this first number here, where it says 1.1. I'm going to replace that with 6,350 and hit enter. All right, there's my answer. Okay, 0.4207. That's the probability that you select one of these households at random and they spend more than $6,350 per year in groceries. So it's a 42% chance of that. For B, it says, how much money would a Western household have to spend on groceries per year in order to be at the 99th percentile? Well, this is an inverse normal problem, isn't it? Because they're giving you the percentile, right? They're saying 99 percentile. That means they spend more than 99%. So I'm just going to go over here, right, to the inverse normal section here. And I'm going to put 0.99 in here, or replace the 7 with 99, 0.99, and hit enter. And I get $9,539.52. That's my 99th percentile. So you can see how easy it is if you set everything up in Excel with all these formulas in the right places. It's so easy to get your answers. You see what I'm saying? You just plug in you just plug in the other numbers and it just flows. So having the mean and standard deviation already set up, ready to go, is half the battle. And you prevent a lot of headaches when you do this, so that you could double check to make sure you didn't make any errors. You could see what the mean and standard deviation is. It's not in the formula. All right, how about, now we have 2 more to do. Both of these are related to the same problem. We're going to start with, and this is a little more difficult problem, but I want you to think about these 2 problems as one problem. 7.36, 7.37. So let me read through 7.36, because again, this one, you really have to read it carefully. It says Clear Company supplies an under-hood emissions control air pump to the automotive industry. The pump is vacuum powered and works while the engine is operating, cleaning the exhaust by pumping extra oxygen into the exhaust system. All right, so something that's being put in there to make the exhaust cleaner. If a pump fails before the vehicle in which it is installed has covered 50,000 miles, in other words, if the car has 50,000 or less miles and this pump fails, federal regulations require that this pump, be replaced at no charge to the vehicle. All right, it's like a warranty. So it's 50,000 miles. This is federal regulations, can't be changed. The company's current air pump lasts an average of 63,000 miles with a standard deviation of 10,000 miles. All right, so there's the mean and standard deviation for all of the air pumps this company produces. The number of miles a pump operates before becoming ineffective has been found to be normally distributed. So this mileage, okay, this mileage is normally distributed. Part A. So actually what I'm going to do now is I'm going to put the mean and standard deviation in. Let's type it right in here. Put 63,000 in here, and I'm going to put 10,000 in here. All right, don't worry about all these numbers because they apply to previous question. All right. First question. For the current pump design, what percentage of the company's pumps will have to be replaced at no charge to the consumer? So what percentage of the company's pumps? That's the same thing as saying what's the probability if you select a pump at random that it has to be replaced at no charge. Well, it's going to be replaced at no charge if it fails, the pump fails, and the mileage is less than 50,000, right? So it's a less than problem. It's asking what's the probability that X is less than 50,000.
Mhm.
All right. So which one? It's this one right here. This is the less than problem right here, right? It's the cumulative. So what I'm going to do is replace the 1.35 from another problem with 50,000. Hit enter. There it is. There's your answer. It's 9.68%. So almost 10%, about 9.68% of the pumps are going to have to be replaced on average. All right. That's the proportion. This company wants to know that, right? They want to know how many. So I don't know if the company considers that a lot or not a lot. All right. B, what percentage of the company's pumps will fail at exactly 50,000? What's the answer?
As you said earlier, 0.
It has to be 0, doesn't it, right? Because it's normally distributed. So you can't answer a question like that because you can't answer a particular value. It has to be a range of values. C, what percentage of the company's pumps will fail between 40 and 55,000? Well, that's this cell here. That's the in between two values. So I'm going to put the upper value, 55,000, I'm going to put it here. And then I'm going to put 40,000 on the lower one here, 40,000. Hit enter. All right, what percentage of the pumps will fail between 40 and 55,000? The answer is a little over 20%, 20.1%. D, or what number of miles does the probability become 80% that a randomly selected pump will no longer be effective? So this is asking the probability of what number of miles. That means the maximum number of miles, right? That number of miles or less. So this is a inverse problem where the cumulative probability is 80%, right? 80% chance it's going to fail. All right. So I'm going to just pick one of these cells here and I'm going to replace it with 0.8. Hit enter. Okay. So at 71,416 miles approximately. That's when it becomes 80% chance it's going to be replaced. Okay. Does that make sense?
Yes.
Yeah. All right. Now, here's the interesting part. 7.37. This one I'll go through with you because it's a little complicated. It says the Clear company in this previous exercise would like to design a more durable pump so that no more than 2% of the original equipment pumps are returned under free warranty. Remember, the answer was 9.8%, previous problem, right? That's what was the prediction. 9.8% of the pumps would fail. Or not fail, but would need to be replaced at no charge. This company wants to create a better pump. That means it has better mileage overall, right? It lasts longer, right? So that only 2% have to be returned. What is that new average life amount? Now, what are they asking here? They want you to come up with a new pump with a new population average, a new mean. That's what they're asking for. So this is a normal with a mean unknown. And they say use the same standard deviation of 10,000. So the standard deviation is 10,000, but we are being asked to find that mean. Now you're saying, what? How do I do that, right? That's ridiculous. How do I do that? Well, they do give you some information here. They do give you that the failure rate, the failure probability is 2%, right? 0.02. We also know that 50,000 miles is the federal guideline for replacing, right? 50,000 or less federal guidelines for replacing one of these units. That's given. That doesn't change. How do we do that? So I'm going to show you the solution. Fancy schmancy solution. All right. So we'll go to my solution here, which I'll post, of course. And let's go to 7.37. So there's 7.36. Put a little asterisk next to this because this is a little challenging. So I'm going to call this random variable y because it's a brand new unit, right? It's different than the previous units that the company created. It has a mean, which is going to be bigger than the 63,000 in the previous problem. We're guaranteed of that, right? That's what they want, something that has a bigger mean. But we have to figure out what that is. Standard deviation 10,000. We're given this information right here. Probability that y, this new unit, is less than 50,000. The company wants that to be 2%. Okay? They are telling the engineers of this company, I want 2%, not 9.8%. That's too big. I don't want to replace 9.8% of the current units. I want you to create a new unit where the replacement rate at no cost is 2%. So I want y to be less than 50,000 to be 2% in this case, not 9.8%. Now, since mu is not known, I can't work with the random variable y here. I just can't. I don't know what the mean is. But I can work with the z. What I can find is the z that represents a percentile of 2%. Cumulative variance to the left of the z is 2%. I can find out what that is using inverse normal. Okay. Let's just go back to the spreadsheet just for a second. And spreadsheet. I'm going to change this back to 0, 1. All right, standard normal. And I want this area to the left to be 2%. So it's going to be 0.02 here. There's my z right here, negative 2.05375, this number right here. All right, forget about these here. This number here is the z where that's the second percentile. All right, negative 2.05375. All right, let's go back to the solution page. Hold on. All right, so that's where I came up with this number here. I just used all the digits. Now, here is now I made a little mistake here. I should change the x to a y here because we're dealing with y's, not x, all right? So I'll make sure I change that before I post it. It should say y, not x. If z is equal to y minus mu over sigma, if that's the formula for converting a random variable, a normal random variable to z, standard normal, then I can simply do some math here and multiply both sides by sigma and solve for mu. Mu is equal to, again, pretend this is a y minus z times sigma. That's what I want. I want that mu. That's what I'm solving for, right? This mu right here. Now I know what y is, right? I know what y is. What is y? Y is 100. The y is 50,000. Okay, the y is 50,000. The Z is negative 2.05375. And what is sigma? 10,000. So I do this little bit of arithmetic here, and I got mu is $70,537.49. Obviously, they're not going to use this number. They're going to round it somehow, right? They're going to round
Right.
it to some more of a whole number. But regardless, this is how you solve the problem. You come up with your mean. So this is here's the point. With a bigger mean, right? 50,000 miles is further away. That means the area to the left is smaller, or a mean that's 70,000 as opposed to a mean that's 63,000. This meets the requirements of what the company management wants them to do. Okay? Not an easy problem, right? Not easy, because you have to think, all right, I don't have the mean. How do I do this? Well, you still can work with the Z. That's why the Z is so important. You can find the Z that corresponds to the second percentile, right? The second percentile. Where the area to the left is 2%. We find it. Then we use it in this formula. Now, if you don't want to do the arithmetic, you could simply replace the Z by this number here, replace the X with 50,000, replace the sigma with 10,000, and then solve from mu. Do a little algebra and solve from mu, and you'll get this number. All right, so this is where you have to sort of be familiar with these formulas. The conversion of a random variable, a normal random variable, to its standard normal. We can always go backwards, right? If we know the Z, we can find the random variable, or we can find anything else in this formula. We can find sigma, we can find the mu. We can find any of these three things. The only thing we need is two of the three. Okay? We only need two of these three and solve for the other one. If we were given mu and we're given sigma, we could solve for x. Okay? So there's actually there's four variables in here. You just need three of them. This is a hard problem because I think for most students, they look at it and they're not even sure what they're solving for, right? They don't even know that they're solving from mu. That's what the question is asking for. It's asking for a new product that has a different mean. Find something else that's better, so that the failure, so that the company doesn't have to spend so much money replacing those units. 2% is acceptable to the company, as opposed to 9.8%. Okay. So I thought this is a good problem to show you, so that you know how to deal with a situation like that. Any questions?
No.
On any questions? No? Okay. So that is it for tonight. The rest of this chapter is unnecessary for the rest of the course. There's another random variable in there called the exponential. And if we were doing some fancy work, fancy stuff, fancy regression. You don't even know what regression is yet, but if we were going to do something that involved the exponential, then it would make some sense to go over. But this is an introductory course. Typically, we don't cover that, the exponential. I'm going to leave that out. I don't really see any reason to teach that to you right now. There's also something in here about using the normal distribution to approximate the binomial. We're going to get back to that later. We are going to be doing something like that later, and that would be the appropriate time to teach you that, but not right now. So what is the plan? The plan is that I will post some homework that will be due probably next Tuesday, all right? That'll be from chapter 7. I'll give you, 3 or 4 problems just to practice. Problems that were not covered tonight. And then next time on Thursday, we're going to start covering chapter 8. Where we're going to talk about now, we're going to start talking about sampling. How do we estimate population parameters, like the population mean, population proportion, things like that, by using sample data? And this is where the theory is going to start coming out of how we do that. And we're going to use the normal distribution. We're going to use it, though, in a different way. All right? It's something a little different than this, because these normal distributions here are for populations, not for samples. So what we're going to do next time is I'm going to show you how to apply the normal distribution when we're dealing with samples. All right? So that's what we'll go with next time. It'll be more theoretical, less numerical for next time. All right?
Okay.
All right. Any questions? No? All right. So I'm going to stop the recording.